Lexing is a professor at Stanford in the math department, and so he's going to give an invited lecture on inverse problems with deep learning. So yeah, thank you very much for giving this virtual presentation. Yeah, thanks.
Okay, thank you, Eric, for the introduction, and thank the organizers for organizing this meeting. This is an unusual time, and hopefully all the internet connection will be working for all of us. Okay, today I'm gonna, Eric, can you hear me well?
Yeah, no problem. Yeah, yeah, it's
okay,
good.
great.
Yeah.
Just want to make sure. Yeah, okay, thanks. Just let me know whenever there's a connection problem. So today I'm going to talk about solving inverse problem with deep learning. And okay, so well, let's start. What is the inverse problem? The inverse problem essentially is trying to discover internal structures from external measurements. So, so some of the examples we're going to visit in this talk is radar imaging, seismic imaging, electron impedance tomography, travel time tomography, optical tomography. So for the three pictures you see here, and hopefully you can see my mouse. The left-hand side is the radar imaging. You can see that there's a radar station which sends signals and trying to detect the target plane. And the second image is a seismic imaging, where essentially you have air guns and signals into the interior of the Earth. And based on the reflection signals, you want to discover what are the structures of the underneath, which we usually cannot see directly. On the right-hand side, this is an image of electron impedance tomography. And obviously the goal here is to try to find a non-invasive way to detect the abnormalities in a child's chest. Okay, so among all these applications, the goal is to find the so-called inverse map, which is essentially take from the boundary measurement data, which I denoted by D here, and trying to find the internal parameter eta. Okay, so depending on different physics, you have different boundary data you collected, and also depending on different applications, you have different eta parameters. So the problem with inverse problem is that one thing is that sometimes depending on the physics that you used, the problem can be quite ill conditioned. And in this case, we typically need the regularization from the data to tell us that what would be the most reasonable internal parameter to discover, even though many parameters will satisfy the physics. Okay. And the other problem, which is main goal why it's connected to deep learning, is because the inverse problem often is a high dimensional nonlinear function. Okay, the inverse map. Because the D data you collected is high dimensional data, and the eta itself is typically a function, is a parameter field. It's also high dimensional, and the map between D and eta is nonlinear. Okay, so this is where deep learning comes in, because deep learning has attracted a lot of attention in the past 8 or 9 years, especially applications in computer science and artificial intelligence, machine learning. So here's some pictures I'm just trying to show that it has been used quite a lot in speech processing, in vision, and also in video processing, okay? And the key ingredients of deep learning, the main object is something called a deep neural network, is what I schematically show here. On the one end, you input your input, and then it's going to be processed through multiple layers of neurons, and which parameterized by certain parameter called theta, and then you're going to output the result. And then deep learning is essentially train the parameter theta of these neurons and trying to make the function give the right prediction. But essentially, that mathematically speaking, what deep learning does is a very flexible representation of high dimensional functions. So this is why it's so powerful. Now, there are a lot of things come together to make deep learning actually work. So one thing is this, so theoretically, people currently view that deep learning is really a very nice and automatic way to do feature extraction. So in some sense, the first few layers of the neural network was actually extracting these features. So compared to all the machine learning algorithms where you have to design features by hand, deep learning allows you to automatically search for these features. Other things which helps quite a bit is one thing is this optimization algorithms like stochastic gradient descent, backpropagation, a very kind of momentum-based method which allows you to search the complicated landscape in a pretty efficient fashion. At the same time, we should not forget about these software support and hardware support like TensorFlow, PyTorch, GPU, TPU. These are the things which really make the neural network work efficiently. Okay. Now, here comes let's try to put that together. So the goal of this talk is to use deep learning to solve inverse problems. And Actually, what I mean by that is that we're going to use deep neural network to represent the inverse map. Okay, so we're going to find an architecture for the for certain application in inverse problem. We're going to find a deep neural network architecture, and then we're going to train to train this neural network so that it may correct predictions. What are the main challenges for deep learning for inverse problems? So, from my point of view, the first thing is that the limited data. Unlike many applications in image processing, imaging, and vision, for example, where you have a huge amount of data that you can collect from the internet, and then you have a lot of people label this data, for example, using Amazon Mechanic Turk. But in inverse problem, for certain application, usually the amount of data you have is pretty limited. Like we often talk about hundreds of thousands or maybe tens of thousands of data samples, input-output pairs, but probably no more than that. And also the inverse problem is typically we're working with a so-called regression problem where the prediction itself is not just a yes or no. It's really, in fact, it has to be a pretty accurate number, right? For example, the material parameter often is you want to say how big the parameter is and how small it is. So we need a numerical number rather than a Boolean yes or no. So this often requires to have a high accuracy compared to some of the vision and AI applications. Okay, so the plan of this talk is the following. So in fact, the strategy is the following. So what we're going to do is that we're going to use mathematics and physics and try to design new neural network modules which are appropriate for our inverse problem applications. So two of these operators, pseudodifferential operator and a Fourier integral operator. I will say a few words about that. Once we have these new modules, what we're going to do is that we're going to assemble them together in the appropriate way to solve a specific for a given inverse problem task. Okay, and finally, we're going to use our limited amount of data to train the weights of these neural network we just built, and hopefully they're going to produce good results. They're going to represent the inverse map accurately. Now, the main advantage of this approach is the first, we have a seamless integration of mathematics and physics and also the data. So math and physics are used to design the architecture of the neural network, and the data is used to decide the parameters. Okay, they help each other. And because of this, sometimes we're allowed to get by with small data size. As I mentioned earlier, one of the main problems is the limited amount of data we have for inverse problems. With this better architecture motivated by physics and mathematics, we're able to, even with small data size, we're able to solve some of the problems fairly accurately. Okay, so we're also going to consider a few applications in this talk: radar imaging, electrical impedance tomography, travel time tomography, and optical tomography. Okay, so that's essentially the plan of the talk. So I'm going to first talk about the new modules, and then I'm going to show you how to use the new modules to solve these inverse problem applications. Correct. Let's motivate the discussion of the modules. So if you take a look at all the successful neural network modules or neural networks that people have been used in the literature, in some sense, there's always some mathematics and physics behind it. So on the right-hand side, I listed the important neural network modules: fully connected neural network, convolution, recurrent neural network, and residual neural network. So convolution neural network is used quite a lot for image processing problems, recurrent neural network for speech processing, and the residual neural network has been essentially most state-of-the-art neural network used. It can be combined with the convolution neural network or fully connected neural network. But if you look behind them, the fully connected neural network has dense operator behind it. Essentially, it's a way to implement dense operator. Convolution neural network essentially is implementing convolution, which is translation invariant local operators. A recurrent neural network, showing this picture here, is essentially representing a Markov chain. Okay, and finally, the residual neural network is the bottom view of it is really a discrete version of the ODE integration. Right, it's a discretization of a semigroup. Okay, so all these neural network has mathematics behind it. So the question we're going to ask ourselves for inverse problem is that, let's take a look at the operator that appear quite a lot in inverse problems. So these are the two of them are called a pseudodifferential operator and a Fourier integral operator. So pseudodifferential operator appear quite a lot because it's the normal operators in inverse problem are typically represented by pseudodifferential operators. And also Fourier integral operators appear quite a lot because if we use waves as our physics for solving inverse problems, and then typically wave propagation is modeled by Fourier integral operators, as we'll see. So the natural question is that given these two commonly appeared operators in inverse problem, what would be the neural network architecture here associated with these operators? Because if we can build a neural network architecture for these operators, and then we can train them, and then we will at least halfway done for inverse problems, right? Because we have the right building blocks. Okay, let's take a look at pseudodifferential operator. So pseudodifferential operator A is it's denoted by A here, is an operator of this form. You can either write it as an integral form in the x and y variable, in spatial variable, but often people also write it as this multiplier form in the Fourier variables. So I'm not going to go into the detail of the pseudodifferential operator, but I only want to point out they appear quite a lot in PDE theory and also in inverse problems. For example, if you work with elliptic operator, fractional operators, and you work with Green's function, which are the inverse of these operators, and if you work with the normal operators, and these are all most likely going to be pseudodifferential operators. So mathematically, the generalization of differential operators, and one important, so what I mean by that is that they have this essential feature of the differential operator, which is if you apply this operator to a function, then the singularity at the result will always be at the same place of the singularity of the input function. So it does not generate new singularities. Okay. So when viewed as a matrix, the pseudodifferential operator has this nice property that, or most of the pseudodifferential operator has this nice property that the off-diagonal blocks of the pseudodifferential operator are numerically low rank. So this allows to be able to represent the pseudodifferential operator in a sparse way, and in very sparse, data sparse way. By considering the off-diagonal blocks, by replacing off-diagonal blocks with their numerical approximations. Okay, so the plan is to find a convenient sparse representation of the pseudodifferential operator, and then to generalize to nonlinear operators. So, there are two ways. In my group, we have explored two different ways to perform this representation. So today I'm going to talk about one of them, which is based on Wavelet transform, and it's something called a non-standard form. And there's another way based on fast multiple methods and hierarchical matrices. But if you're interested, we can talk about that at the question or offline. All right. So what is this wavelet-based method? So this is based on something called a non-standard form of the wavelet representation of pseudodifferential operator. This is proposed by three mathematicians, Greg Belkin, Rafi Kaufman, and Vladimir Rokhlin. By now it's probably about almost more than 25 years ago. Okay, almost close to 30 years ago. So the idea of this is the following: that if you give me another differential operator A, written n by n, written by this gray matrix, because of this low rankness of the off-diagonal blocks, you can actually write this in a product of three matrices. So first a fat matrix, a big matrix in the middle, and tall skinny matrix. So the first matrix and the last matrix correspond to this so-called redundant wavelet transform. So typically the way wavelet transform we understood is that it's a orthogonal transformation. At least it's a one-to-one map, the number of degree of freedom the same. But this special transformation is going to keep all the wavelet coefficients and the scaling coefficients together. So that's why the size is increased by a factor of 2. And the middle matrix is something called a non-standard form. You see that it has this finger patterns which at all scales. So at every scale, it's actually the interaction within every scale is very factorly encoded by these three diagonal dominant matrices. So if you do some thresholding, they really become three diagonal matrices. Okay. So you do it for every scale and you multiply them together and you get a good approximation of the original operator. That's the main idea of the BCR, Belkin, Kaufman, Rokhlin scheme. So why does it link with neural network? Well, the reason is because if you take a look at the computation at every single scale, so for example, you take a look at the finest scale, this biggest block, and consider the interaction of multiplication, the contribution of this block, so to this matrix. This will correspond to take this first two, for these two blocks, multiply this one and multiply this one, okay? So this is what I'm written down here. So in fact, it's not hard to see that this can be actually encoded very nicely with the neural network architecture. So if you apply to an input vector, So this will correspond to a 3-layer network. So the first step is just doing multiplication of these two diagonal matrices. Assuming these operators translation invariant, then this becomes a convolution, okay? Taking one channel to two channels. And the middle operator itself is also a convolution from two channel to two channel. And finally, you have another convolution from two channel back to one channel. So this is the neural network architecture for single layer. To get a whole neural architect algorithm, so what we need to do is that we need to just put all these layers together. So this is corresponding, the top line is corresponding to the finest layer. And then, so once you have these wavelet coefficients, you're gonna use these scaling coefficients and then do it for the next layer and so on and so forth. Here I only showed you 3 layers, but for large problems, you can have quite a lot of layers, log n of them. Now, well, this is just a BCR scheme, Belkin, Kaufman, Rockling, but how are we gonna make it into a neural network? The idea is simply just to insert a few more internal layers and then add values to introduce a nonlinearity. So this will give us a nonlinear version of the pseudo. Okay. Now, second, let's talk about this so-called Fourier integral operators. So Fourier integral operators is typically written in this form. It's much easier to talk about this in the Fourier representation. So it appears quite a lot whenever you have a wave propagation and you work with hyperbolic problems. Okay. Okay, it's a generalization of the Fourier transform, and which means that it has a certain very nice features. Which means is that when you apply to functions f, okay, so the singularity of the f will move instead of fixed at the same point. It's actually going to move around a little bit, but the way to move around is actually in a very well-defined way. It's called a Hamiltonian flow. Okay, essentially tells you how the singularities of the propagate along the characteristics of the wave equations. So when viewed as a matrix, these operator has a very nice property, which I call a square root size blocks a numeric low rank. I will show you in the next picture what I mean by that. So based on this nice low rank property, what we're gonna do is that we're gonna represent this Fourier integral operator again in a very sparse way, which is friendly to neural network. Okay, so that we can actually implement as a neural network and then generalize to nonlinear versions. So what do I mean by that? So suppose you give me a neural network of, you give me an operator of size n by n, Fourier integral operator. So we're going to partition into square root of n by square root of n blocks. Each of the block itself is also square root of n by square root of n. This property I talked about essentially ensures that if you take each of these tiny blocks, this block itself can be written as it's a low rank matrix, has a low rank approximation, numerical low rank approximation. So each of the block can be written as a tall skinny matrix times a small square matrix times a fat matrix. Okay, so you do that for every block. So the second picture here is just trying to show you that I perform this low rank approximation to all the blocks. But if you think about, look at for a second, so this matrix itself can be written as the product of 3 blocks, 3 matrices. The first matrix just collect all these column tall skinny matrices together, okay, according to which low row they belong to. And the last matrix take all these row fat matrices together. And final matrix, which I call switch matrix, is just trying to tell you which column interact with which row. Okay, it has a fixed pattern here. So this is what we call switch matrix. So in some sense, you can think about this is really doing some information processing on the row space, and then you're gonna and you then perform a certain switch operator, and then decipher this information at the column space. So here I'm just showing you the simplest version of this so-called butterfly factorization. There's a hierarchical butterfly factorization, which is more involved, but we're only gonna use the simplest version for the time being. Okay. Now the next question is, well, suppose you give me this approximation. How do I translate it into a neural network? The idea is very simple. It's because if you take a look at applying these butterfly factorization into a certain input vector, well, this can be written as a 3-layer neural network as well. So the first one is gonna do this so-called either it's a locally connected operator, or it's like a convolution operator. So essentially, what you do is that you take this vector, you transform it into 2 dimensions. One is going to consider as a channel, the other is going to consider as a spatial location as well. And then if you perform a convolution, and so it would translate this into a 2D data where one dimension is going to be channel and the other dimension is going to be much smaller because it's only square root of n in size. And then the middle operators, what that does is really does the transpose of this matrix plus some diagonal multiplications. And the final operator itself is undo what the first operator does, is take this short multi-channel data and put it back into a one-dimensional data. Okay. Now, so this is really the neural network architecture for this so-called switch butterfly factorization. So in order to make it more flexible to handle nonlinear operations, so what we do is really just introduce a few more layers like all neural network people do, and also include the ReLU functions and to inject nonlinearity. So this is something we call SwitchNet. Okay, so this is the first part of the talk. Let me remind you that we spent about maybe 15-20 minutes introducing these new modules. One is called PCRNet, the other is called called SwitchNet. And now we're going to try to use it and combine them with some convolutional neural networks, try to solve some inverse problem applications. So so here we're going to consider quickly consider 4 applications. So one is radar imaging and electron impedance tomography, travel time tomography, and optical tomography. So in each case, what we do is that we design a neural network architecture for this inverse problem, okay, for the inverse map of one of these problems, and each of these problems, and then we're going to train the neural network weights end to end from the data we have, okay. So and finally, once you train that, the neural network can use for prediction for new incoming data boundary measurement. So let's go through each of these applications quickly. The first application is something we call radar imaging. So there are various different setup of radar imaging, but here we consider only the simplest setting, which is in the so-called acoustic scattering. The real radar imaging is the electromagnetic, but to simplify, let's consider acoustic. So the physics is modeled by this equation called the Helmholtz equation, which is operator LU is equal to minus subtraction minus omega squared over c squared. U is equal to 0. So here U stands for the total field. It's the unknown sound speed. Okay. So the total field U actually has 2 parts. One is this incoming wave field, which comes from this direction, which is typically a plane wave in the S direction, for example, here. And then the scattered wave, it could be in any directions. Here I'm only drawing the scattered wave in one direction R, but it could actually go anywhere. Okay. So this is denoted the scattered wave denoted by US. So in most of the radar imaging applications, so the sound speed has a background velocity. Okay, this is denoted by C0. So in vacuum or in air, the C0 is just a constant. You can think about to be 1. So therefore, the unknown quantity Cx, in order to solve this unknown quantity Cx, which is the variable coefficient, the variable sound speed, it's equivalent to consider this quantity called eta, which is essentially remove the background part. Okay, so this is called eta. So now, so this is eta is something that we're trying to discover. And what are the boundary measurement? Well, the boundary measurement is actually a scaled version and modulated version of the scattered field at all possible directions. So the mathematics also in physics, there's a name for it. This is something called far field pattern. Okay. So the data is a far field pattern for all incoming directions, for all outgoing directions. And the inverse problem we're going to consider is that from this so-called far field pattern, and we're trying to discover the eta, which is the material, unknown material property. So I saw that Eric, one of Eric's students, is probably going to talk about here. We assume the full data. Okay, we'll consider all directions, incoming and outgoing directions. But I saw that Eric has one student is going to talk about the partial data. So this is also something extremely important. But here we consider only the full.
Yeah, just to know the partial data is kind of in a different context, but.
Oh, I see.
Yeah,
okay,
it's
all right.
somewhat different, but yeah.
Okay.
Anyways,
so but here we have collect all possible data directions. All right. So well, let's just try to do some little bit math here. So instead of solving the inverse problem, let's just take 1 minute to consider what would be the forward problem, which is mapping from material property to the boundary data measurement. So after doing a little bit math, we realize that if the media perturbation is not so large, so we're using linear regime to motivate the design of our architecture. So if the media perturbation is not large, then the boundary measurement is related to the perturbation, media perturbation in this very simple integral form. Okay. Now this looks somewhat like a Fourier transform, right? So in fact, it's not exactly Fourier transform, but very close. But the most important thing is that this operator itself is actually an FIO. So that the FIO between two domains. One is this X, the spatial domain, and also the second is this RS domain is S1 cross S1, just because a unit circle in 2D, right? So the operator itself is actually a Fourier integral operator between these two domains. So this allows to use a switch net to represent A. Now, if you take a look at one second, that what if we adjoint of this operator? It will just be replace this phase function by a minus sign. So that will also be an FIO. So therefore, the adjoint of this operator can also be represented by Fourier integral operator. And so we can also use a switch net to do that. Now this here's a, okay, now let's look at how do we do the inverse problems. Well, the inverse map is from D, the data, to the material property eta, right? So our architecture is motivated by this very simple algorithm is called filter back projection algorithm, which works well for linear case. But we're going to use the linear case to motivate the architecture. But then since our neural network was nonlinear by injecting multiple internal layers, so and trained from data, so our architecture actually can handle nonlinear case. But let's just motivate the discussion with the linear case first. So the filter back projection algorithm says that in order to get back to E, so what we can do is that we can just solve this so-called pseudo-inverse, right? The regularizer pseudo-inverse. So we take the D multiplied by the adjoint operator and then inverted this so-called normal operator, and then we're done. Now A star itself is a Fourier integral operator. So as we said, we're going to use a switch net. This A star A plus this is a pseudo-differential operator. So we're going to use the PCRNet. So therefore, the architecture is going to be really simple. Is that to take our D, the input data, as a bunch of data, we're going to use a switch net to implement A star, and then use a PCRNet to implement this inverse here, and that will give us eta. Now, even though this is, as I said, it was motivated by linear architecture, because we make it very rich by including internal layers and the ReLU nonlinearities, this architecture is able to handle quite reasonable nonlinearities. So finally, we're going to train all parameters from end to end using the data samples, and this will give us a neural network. So here I'm just only showing you one single example because I have quite a few applications. So this is one case where you can see that you have 4 different inclusions, points inclusions, and then this is the far field pattern you obtain. Okay, so this is the ground truth eta, and this is the ground truth far field pattern. This is the so the inverse problem is that take this far field pattern and try to recover this. So here is the neural network results. You see that visually it's the same as the ground truth. Okay, so here we use a little bit more than a 10,000 eta boundary and internal data to perform the training testing, and it's quite acceptable for this application. Okay. So the second application is called electrical impedance tomography. In the case of electrical impedance tomography, the equation is really given by a diffusion equation, so elliptic operator. So here's the setup. So you have a rectangular domain. So horizontal is X and vertical is Z. And then you, let's say you specify 0 boundary condition at the end, and then you have, and the top space, you have I will describe the boundary condition. So the operator is minus Laplacian minus eta. So you can think about eta to be some kind of potential perturbation, which is unknown. Okay, the goal is that to try to discover what the eta is. So the physics goes as follows. So in our experiment, what we're going to do is that we're going to put a delta source. So specify the boundary condition to be 1, and then then we're going to solve for the solution. So if you call this source point S, where I specify the delta boundary condition, and so the solution I will denote by US. Then what I'm going to do is I'm going to measure the normal derivative of the US at all the boundary points R. Okay. So if I iterate through all sources and all boundary measurement, I'll have this 2D array, which is called Dirichlet to Neumann map. Okay. so which I denote by D here. Now, the inverse problem is that given this boundary measurement, the directional Neumann map, I'm trying to discover what would be the internal media eta x. Sorry, it should be eta xz here, okay? So again, let's do analysis. After you do a little bit calculation, you realize that, okay, first let's consider the forward map, which is a perturbation from eta to this, this boundary data measurement. So if you do a little bit calculation, in the linear regime, you see that there's a very easy relationship between eta and d. In fact, d is given by this integral operator or summation operator, which multiplied by eta. Now, the beautiful thing about this is that this operator A itself is a hidden convolution. So in fact, it's not too hard to see, because in the previous picture, so if, for example, when the Laplacian operator is translation invariant, so therefore in the linear regime, so the whole, Green's function, the whole directional Neumann map should be translation invariant. So therefore, that's why the D itself is translation invariant, okay? So, but the translation invariant only happens in the horizontal direction. So this is what I'm trying to show here, is that if you write the problem not in terms of RS, the receiver and source coordinates, but in this middle point and offset coordinate. So here's the relationship. So receiver is middle point plus edge. The source is middle point minus edge. Edge is offset. And if you regroup the data D in this MH coordinate, you see that this can be written in this following form. And this is clearly a convolution in the MX variable, where the H, the offset, and the Z variable, depth variable, serve as the channels. So what this means is that this A map, which is the forward map in the linear regime, can be written simply represented by a CNN, for example. 1D CNN goes with multiple channels. Now, for the inverse map, we perform the same calculation, the same analysis. We're going to consider the feedback projection, and the A star operator, as we said, is similar to A, can be represented with 1D convolution neural network. The adjoint operator, the inverse of the normal operator is a pseudo-differential operator. It can be represented with BCR. Now, one thing I didn't emphasize is on the previous slide is that because the diffusion nature of the EIT, so you can perform a lot of compression in the depth direction, also in the offset direction. So this is also what we do here. So for the inverse problem architecture, when we take the data, we first perform the compression in the H variable, and then do 1D neural network, CNN, and then decompressing the Z variable, and then eventually go through a PCRNet to get the eta back. Okay.
Oh, just a quick question: the compress, it's a max pooling, or it's what is it?
It's just it's a linear reduction. It's a linear projection. So it's just a matrix. And it's among the channels, matrix. And it's a fully connected.
Fat matrix, I see. Okay.
Yeah, it's a fat and tall skinny matrix, depends on compression of, fat matrix for compression and the tall matrix for the decompression. Right. Okay. Yeah, so this is the, okay, so I will just quickly show you the result. So in this case, we have, in fact, in this case, we consider the measurement both on the top and bottom surface. Okay, so the picture is slightly different, but the physics is exactly the same. So here is the etas with our inclusions. It's 4 different Gaussians in different part of the domain. And this is a very ill-posed problem because it's a diffusion problem. So therefore, typically there's no unique answer, at least no unique answer numerically. So we train this with 8,000 training pairs. And this picture is trying to show you, this is the reference solution. And this is the boundary measurement that we received on the top and bottom surface in this middle point of reference coordinate. And this is what we reconstructed. As you see that visually they are almost the same. This is quite remarkable for EIT. And the error in this case about 8%. All right, let me quickly move to 2 more applications when the travel time tomography, okay? So I forgot to mention, these are, most of them I work with my previous postdoc, Yu Fan, and who did a great job on all these things. So in the travel time tomography, the physics is the following. So you have an object, think about this, in this case is a disk. And the thing you're gonna measure is that you put a source at a certain point, and then the source is gonna maybe provide some kind of sound wave. And at every point on the boundary, you're gonna detect what is the first arrival time for these when the wave reaches a certain point, boundary point, okay? So because the media inhomogeneity of the internal media, so the wave does not propagate along straight lines. Like the Huygens principle tells you that the shortest time is going to search a path, which you try to go to the places where the speed is fast. Right, yes. And so this is governed by the so-called Ikono equation. So this grad u is equal to 1 plus mx. The 1 plus mx is something called the slowness. Now, the inverse problem is trying to discover this slowness mx from boundary measurement. And this boundary measurement is something that I just described, is that for every source point on the boundary, what you're going to do is you're going to start some pulse, and the wave is going to propagate. And at every receiver, just record how much time does it take for the wave from the source to propagate it to the receiver. Okay, and so all these data, again, full measurement is recorded into this table called a DRS. Source is where you send the signal, the receiver is when you receive the signal, and D is how much time for the wave to travel from R to S. So the inverse problem is trying to go from D to recover the slowness, unknown slowness. So here's the analysis. So again, we consider the linear regime and just to motivate architecture design. So in fact, if you consider the media D, but not in the source receiver coordinate, but in the source and source plus offset, H is the offset, meaning that how much angle you sweep from S to R. And you consider the media M not in the usual XY coordinates, but in the so-called polar coordinates. By using this, so here we consider a simple setting, which is the domain is a circle, right? Here's a disk. So using the rotation symmetry of the disk, so in fact, you can write down this D, the data dependence on the media in this simple convolution form, okay? So it's a 1D convolution in the S and the theta variable, this angular variable, and where H and rho are treated again as the channels. So this means that we can also use 1D CNN with multiple channels to represent this forward map A. Again, the rest of the discussion is the same. We're going to use a 1D CNN also for A star, and we're going to use the BCR for this inverse of the normal operator. And when we put everything together, we get a neural net architecture. And once we have the architecture, we just train it. Okay. Now here, let me show you some results. So this is the experimental setup, and MX is the unknown media that we're trying to discover. So in this synthetic data, MX is given by a group of ellipsoid inclusions. So at most of the places, the M is going to be 1, but at these inclusions, M is going to be sometimes bigger than 1, sometimes less than 1. So we trained this with about 20,000 pairs of media and data pairs. And here, just give you a flavor about how numerical results look like. So in the first row, we train only with the negative inclusions, meaning M is less than 1. In the second row, we train only positive inclusions, which is greater than 1. And then finally, we train a slightly more challenging case where you have both negative and positive inclusions. So the first column is the reference. You see that this is what the true solution should look like. The second column is what we get if we don't have any noise in the boundary measurement. So you see that visually these two pictures are exactly the same, even though the problem is a yoke post, okay? And this column shows you where we have injected 2% of the noise in the boundary measurement. You see that we also get a fairly good picture. There's a location, the shape are exactly right. The last column shows you that even with 10% of the error, noise in the measurement, we can still faithfully discover the location and the shape of all these inclusions. Even though the boundary and the shape becomes a little bit fuzzy, but you see that we get the location and the shape, compared with the reference, we get the location and the shape accurately, okay? So finally, let me just briefly talk about the last application, which is optimal tomography. So in the case of the optimal tomography, the setup is fairly similar to travel time, but the physics is a little bit different. Again, you have the unknown inclusions in your certain medias, and you have the source on the boundary of this disk, and you have the receiver on the boundary. This is a typical setup. So the physics is given by the following equation. Is something called radiative transfer equation. So the quantity you care about is not this travel time anymore. Is this something called a phi? The phi is actually tells you at a specific location X are traveling in that direction. Okay. So this is a quantity which defines the whole domain, which you cannot direct access. But what you can do is you can do the boundary measurement. Okay. So here, the mu here is something called a scattering coefficient, is something that we do not know and we're trying to figure out. So typical experiment is done this way. So at every boundary point, what you do is that you're going to inject a delta source. Okay, so it's going to be a delta source either going one single direction, or delta source meaning that's a source at a single point. And but light can either go a fixed direction, which is going normal direction inside the domain, or you can have an angular diffusive source, which meaning that the light is going all possible 180 degrees going inside the domain. Okay, so both works. But what is the boundary measurement? So the light is going to propagate the domain and bounce back and forth, and eventually going to reach the boundary. At every boundary point R, what we're going to do is that we're going to do an angular averaging. So we're going to average over all the light going from all possible direction to this receiver point. And then we're going to integrate it and sum them together, and we call this quantity B. So the boundary data, the data we define is that what would be the B quantity we receive at the receiver R if the light is injected at the location S. Okay, this is BSXR. This is our boundary data, measurement data. So mathematically, in physics, this is called albedo operator, and this is the data we can collect. And the whole goal is for the inverse problem is to take this albedo operator D, and then the diffusion, the scattering coefficient. So in fact, the analysis is actually fairly similar to the travel time tomography. In the linear regime, the math is going to be slightly more complicated. If you're interested, you can take a look at our paper. But at the end, due to this rotation invariance, this albedo operator D that you can calculate in this against this offset coordinate. So we write this D in terms of these source and offset coordinate, where the offset is the difference between receiver and source. It actually depends on the mu in the polar coordinates, again, through this 1D convolution fashion, where the convolution in the S and the theta variable, the angle variable, and the offset h, and also the rho, the radial variable, as treated as channels. So this means that the forward operator can be represented as a CNNN. So now for the inverse map, again, the same architecture. So A star also represented a 1D CNNN, and this inverse of the normal operator is represented by a pseudodifferential operator. So it can be represented by a PCRNet. Okay, so that's our architecture. It's the same architecture. So it's kind of, I mean, it's the same architecture for different inverse problem applications. In fact, that's not so surprising, because if you think about image processing and imaging vision applications, there are many different vision tasks, but the convolutional neural network work for all of them quite well. So this is also something similar here. So as long as you have rotation symmetry, work quite well. So finally, let me show you the results here. So again, this is the setup. And the mu inclusion in this case is a group of ellipses included in the domain. So we train again with roughly 8,000 samples. And this is one result that we have. So this is the reference mu. And this is the neural network. This is what the neural network recovers from the albedo operator when you have no noise. So this is what happens when you have 0.5% of noise, 1% of the noise, 2% noise, and 5% of noise. So for optimal tomography, 5% of noise is really already very high. So for classical methods, it's usually quite hard to achieve a reasonable result. But you see that we get the location exactly right, and also the shape of the inclusion is also quite accurate. Okay. So here's a quick summary. So in this talk, we talk about two things. One is we introduce new neural network modules, which are appropriate for inverse problems. Two examples we discussed as pseudodifferential operators. This give us PCR, and the Fourier integral operators give us this switchlet. Okay, and we also talk about for different applications. So the takeaway message is that invariance considerations often suggest quite effective neural network architectures. And what we did is to use the math and physics to decide the structure, and then the weights of the neural network, the parameters of the neural network are decided from the data. Okay, This allows us to work with a rather small training data set. And when with end-to-end training, this give us quite accurate result for all these inverse problems. So here's the reference, the papers that describe the things that I talked about. This paper is talk about SwitchNet. This talks about PCRNet. And these 4 papers talk about these applications I discussed. But this paper also has the application that I talk about, the radar imaging application. Okay, finally, you can find all these papers. Back to Eric.